This is the second lecture in chapter 14 in our look at acids and bases. In the first lecture, we looked at Arrhenius acids and bases, which are pretty broad categories and are based on the presence of either a hydrogen or a hydronium ion or a hydroxide ion. In this lecture, we're going to look at two other definitions for acids and bases. So the first one revolves around two gentlemen, a Dane and an American chemist, Bronsted and Lowry, who were working on in a variety of different branches of chemistry in the 1920s, about the same time as lots of other chemistry was happening and a lot of advances were being made. So Bronsted and Lowry were doing very similar work, and they both came up with a different definition for acids and bases than the one that Arrhenius had used. In the Bronsted-Lowry definition, an acid is any molecule or ion that donates a proton. So remember that a proton is a positively charged particle. And with the Bronsted-Lowry acids, most often the proton that's being donated is a single hydrogen ion. Remember that hydrogen has an atomic mass of 1. That's because hydrogen only has a single proton in its nucleus. There's no neutron there. So the movement of a hydrogen ion is, by definition, the movement of a proton. So obviously hydrogen fits in that category. It is itself a proton donor. There are lots of other elements not elements, but molecules and compounds that will also donate a proton. Nearly all of the Arrhenius acids fit in this group, HCl and H2SO4, for example. But interestingly enough, water, which is not an Arrhenius acid, water also fits into the group of Bronsted-Lowry acids because it can, in fact, give away a hydrogen ion or a proton and leave behind a hydroxide ion. In the Bronsted-Lowry definitions, a base is any molecular ion that accepts a proton. So ammonia is an easy example. If ammonia and a hydrogen ion come together, you end up with the ammonium ion, which we've seen in quite a few of our chemical reactions and compounds. Many of the Arrhenius bases will fit in this group, but many of them will not. Actually, let me say that again. Few of the Arrhenius bases will fit in this group, but many of them will not. Because remember that the Arrhenius definition requires the formation of a hydroxide ion, and many of the compounds that have a hydroxide, many of the inorganic salts that are a metal and a hydroxide, do not necessarily want to accept a proton. They won't necessarily bond with a single hydrogen ion, for example. So they don't fit the Bronsted-Lowry definition. However, the hydroxide group itself, the hydroxide that forms from an Arrhenius base, will very easily accept a hydrogen ion, right, to form water. So the hydroxide group is a Bronsted-Lowry base because it will easily accept a proton to form a new compound. The very broad definition of a Bronsted-Lowry acid-base reaction is any one in which a proton is transferred from one place to another. In most cases, this transfer obviously would be from an acid to the base. So remember that the Arrhenius definition of an acid-base reaction is one in which salt and water are created. A Bronsted-Lowry acid-base reaction is one in which a proton is transferred from a reactant to a base. So the acids that you will see in the Bronsted-Lowry category are very similar, and many of them overlap quite successfully with the Arrhenius acids. They are sorted. Remember, the Arrhenius acids are kind of classified based on the anion, whether the anion is single like a single chloride, or whether it is, say, polyatomic, like a sulfate, for example. And these are also seen in the Bronsted-Lowry acids. The Bronsted-Lowrys, however, are classified by how many protons they can accept, how many protons they can donate. And so we've got a whole big group here we've got hydrochloric acid, we've got nitric acid, we've got that one would be, perchloric acid. All of these have a single hydrogen as part of their formulas, and so they are called monoprotic acids. They just have a single proton that they can donate. Mono means one, prot means proton, so a single proton can be donated. When that happens, let's say HCl donates a proton, so now you've got a proton, which then reacts with water in an aqueous solution to form a hydronium ion and then an anion. There are also acids that can donate multiple protons. In this case, we've got sulfuric acid. There's 2 hydrogens there, so it's called diprotic, di for 2. Or in the case of phosphoric acid, we've got 3 hydrogens, so that would be triprotic. Any acid that can donate more than 1 proton is polyprotic. Poly just means many, so we're donating many protons, 2, 3, etc. This donation happens individually. So, for example, when phosphoric acid breaks down, a single proton is donated, and then we are left with an ion that contains the rest of the elements in the group. And then a second reaction will occur where this ion will donate another proton, and then you'll have another ion, and etc., until eventually all of the protons are donated. The first donated proton is the easiest. That one happens very quickly. It's highly reactive, and then each resulting anion is acidic still, because it still has protons to donate. It's just not as strongly acidic as the original neutral compound would have been. Okay, our final definition for acids and bases comes from an American gentleman by the last name of Lewis. He was working in chemistry at about the same time as Bronsted and Lowry in the mid-1920s. He, however, is known mostly for his work with electrons. He came up with a model, and it's called the Lewis dot structure. His model represents where electrons are found at any given time in space relative to the nucleus of the atom. And so what he said is it is most likely that electrons will pair up and then be as far apart from all the other electron pairs or single electrons that are moving around the nucleus as possible. So, for example, here you see a chlorine atom, a model of a chlorine atom, and we know that chlorine has seven valence electrons. Lewis represented the location of these valence electrons by using dots. A single dot represents a single electron. A pair of dots represents a pair of electrons. And so he showed the location of the electrons in this manner and showed that this pair on the left is as far away from all of the other electrons as is physically possible. And this pair is as far away and this pair is as far away, and this single one is as far away as it can get from all the others. This model is called a Lewis dot structure. And because Lewis's focus in chemistry was on electrons and how they behave and where they can be found, you might expect that his definition of acids and bases includes the mention of electrons and is in fact centered around electrons. So the Lewis acid, he said, is any molecule or element that accepts a pair of electrons in order to form a non-ionic covalent bond. So for example, let's look at the hydrogen ion. In this case, the hydrogen ion has no electrons, right? None at all. And in order for it to be as stable as it can be, it needs to have two. It wants to be like helium. Helium's the nearest noble gas. So the hydrogen ion will very easily accept a pair of electrons from somewhere else in order to get its noble gas configuration, in order to have a neutral, there we go, a neutral structure and a noble gas configuration. And so that hydrogen is by definition a Lewis acid. It will accept a pair of electrons. In doing so, just like if you accept a loan from somebody, you are now kind of bonded to that person, right? You owe them something and they will at some point collect that loan back from you. That's the way it works in chemistry too. At some point, those electrons can be returned to their original owner. And so in doing so, a bond is formed. And we get this, what's called a covalent bond, because these two elements are sharing valence electrons. Co means to share, valent means valence electrons. So when hydrogen accepts a pair of electrons, say from this chlorine atom, it forms a bond with that chlorine atom. And that bond holds those two together now into a single compound, which in this case would be HCl, or hydrogen chloride. We know it as hydrochloric acid. So the accepting of a pair of electrons in Lewis's mind defined an element as an acid. As you might expect, this is a really broad definition, and it doesn't have a whole lot in common with the other two acid definitions that we've looked at so far, but it does share quite a bit of overlap with some of those other definitions. As I bet you might have been able to predict, a Lewis base is just the opposite. A Lewis base is one that does the donating of an electron pair. So in this example, chlorine would be our Lewis base because it was able to donate that pair of electrons to the hydrogen. And so taking those two definitions together, a Lewis reaction that involves acids and bases is any one that takes place between an electron donator and an electron acceptor. And it has otherwise virtually nothing to do with ions, where the Arrhenius definition was very heavily focused on ions, and the Bronsted-Lowry definition was very heavily focused on protons. Now we're dealing with a definition that's very heavily focused on electrons. What's important to remember is there is a lot of overlap in many ways between these three definitions, but they each focus on a slightly different area of the atom and the way that it behaves. So if you would, please bring 3 discussion questions to the next class and write a summary, and I will see you soon. Thank you.